Tootsie Roll Pops. A lab report by Eli Lee, Sam Gordon, and Alex Lee. So how many licks does it take to get to the center of a Tootsie Pop? We don't know because the project didn't answer that question. But we did find the rate at which the lollipop got smaller. So our first step was to measure the lollipop for its radius.
Yep. So first we measured the diameter, which is 2.8 centimeters from side to side. Dividing that by half, or rather dividing that in half,
Or
gives us,
multiplying by half.
indeed, gives us a radius of 1.4 centimeters from the center of the lollipop. The difficulties we had were, well, measuring this lollipop. It was very hard to get a precise measurement because lollipop is round and we were trying to hold it against a flat ruler. But we avoided this problem by switching to a translucent plastic ruler, so we were able to observe the outline of the lollipop directly through the measuring instrument.
Which allowed for much more precise measurements of said lollipop.
Yeah.
So we did 11 trials. We had our initial radius, and that was our final radius.
Yep.
So the lollipop shrank a bit each time.
Yep, 30 seconds of sucking.
For each trial.
Indeed.
So
yeah.
Then our next step was to put this data into a calculator to get an equation.
Yep, and we just used the statistical function on the calculator.
And it was a correlation coefficient of 0.998.
Yeah.
Which meant that it was
pretty good.
Very good.
And it turned out to be a cubic function. We actually used the quintic function, but the r to the fourth power value was infinitesimally small, so we just disregarded it.
It was point something times 10 to the negative 8 or something like that.
Yep.
So in order to find the derivative, we just did standard derivative rules. So we ended up taking the cube, the first number, and it was cubic, so we multiplied it by 3, then moved that down. Same for that and that.
Yep.
Which
and then we got rid of the
smallest
constant,
number, because the derivative of a number is 0.
Yep.
Then we plugged that into the volume. You can explain this thing.
Yes. Okay. So next step was to find the rate at which the lollipop's volume was changing when the radius was at 3/4 of a centimeter. So first step was, of course, finding the volume equation. So the volume of a sphere.
Approximate sphere.
Yes, because the lollipop was slightly lumpier. But anyway, volume of a sphere is 4/3 pi r cubed. So taking the derivative of that, you get 4 pi
because 3 times 4 gives you 4, then pi, and then
well,
that's
3 times 4/3 equals 4.
Yeah, exactly. And then times the drdt, because we're doing implicit differentiation.
Oh, yes.
So what we ended up doing is if r equals 3/4 and ddt...
Yep, just plugged in the values, and we eventually got at 3/4, at r equals 3/4, we got a declining volume of losing 1.262815536 cubic centimeters for every minute of suckage.
Yeah, and the 3/4 was the owl's given rate, which was proven to be
the given rate was 0.08 cubic millimeters, which is nothing. So owl was wrong.
Owl was wrong again.
Yes. The end.
Finn Barclay.